My name's Matt Nowell. I'm the EBSD product manager here at EDAX. And today I'm going to be talking about some new developments in EBSD detector technology. And so, just to give you some idea of what I'm going to talk about, a little bit about EBSD detectors in general, some of the signals and signal processing we do to enable good EBSD collection, introduce our new Velocity EBSD camera based on CMOS detector technology, then talk a little bit about direct electron technology. I'd like to acknowledge a lot of coworkers and colleagues who have helped build this: Stuart Wright, Renee DeClos, Sean Wallace, and Patrick Camus from EDAX, Seiichi Suzuki-san from TSL Solutions, and Gran Meaden from BLG have all collaborated to try to make this happen. So it's kind of exciting for us. So I don't know how familiar you are with EBSD, but I'll start just by saying there are two main application areas. There's when we collect a single pattern, and in that situation we're doing things like phase ID or trying to decide if something's crystalline or amorphous. And then there's EBSD mapping, which we call OIM, or orientation imaging microscopy, and things like high resolution or high angular resolution EBSD. Generally, when we collect an EBSD pattern, we need to be able to detect the diffraction bands for automated analysis. You know, we try not to do manual work. And of course, when we're doing this, the speed of acquisition is primarily important for mapping applications. So for phase ID, this is a lot of point and click work where we point and click in different grains. We figure out what the crystal structure composition is to determine the phase. For orientation mapping, we're clicking on multiple grains and multiple points within a grain to figure out what the phase and crystal orientation is as a microstructure. For EBSD mapping, this is where the system is coupled and we measure along a known sampling grid. So we have an array of points where at each point we collect the pattern, we analyze the pattern through what we call a Huff transform to find the position of those diffraction bands. The position of those bands then tell us the crystal phase and crystal orientation. We repeat that for each point. We're able to create maps based on that data. So when we do this, my personal goal is to say, can I index 100% of those points? That's the goal, right? We don't want to fail if we don't have to. And it's generally possible in a lot of materials. So this is showing from a rolled aluminum sample, a hexagonal titanium alloy, and a deformed ferritic steel. We're pretty close to 100% of the points that we can index successfully and with high confidence. So there's two questions of when we don't reach 100%, trying to understand why, and more for the role of this talk, what role does detector performance and setup play in affecting indexing performance? Because as we develop technology, we want to, meet or exceed current performance benchmarks. So to give just a little idea of history, these are some of the earliest, what we would now call EBSD patterns collected. So this was, almost, I guess it'd be 90 years ago now. Some of the first patterns were shown. These were collected with film, obviously slower collection time, single point collection, a lot of the work involved with processing film, and we'd get intensity gradients, we'd get image distortions from how that was projected. And so this was how it was done for a number of years, just looking at single patterns, looking at phases and things like that. Really the breakthrough for EBSD as a technology was coupling the cameras to computers, so you can start to use online analysis of the patterns. This was done using what were called SIT, or silicon intensified target cameras. These were analog cameras, so the speed were limited by analog TV frame rates. And that then coupled to what we'd call a modern EBSD system, where we've switched to digital sensors. So we want to get a signal into a camera, into the computer for analysis. So modern systems, we have a phosphor screen, we have a lens to focus the signal from the phosphor onto the sensor. Traditionally, we've used CCD-based sensors. That's been a standard for since 2001. We have a slide to position the phosphor screen, and then we have a bellows seal to keep that under high vacuum conditions as we translate the detector. One of the questions I often get is, why do we have a round phosphor? Basically, that's the shape of the diffraction signal. So you can see as I increase the intensity on the camera, it's a radial signal, so we're able to match the shape of our detector to the shape of the signal. It allows us to optimize the dynamic range of the camera by having the signal from the center to the edge sort of symmetric with the detector, and we don't have to make any adjustments in the huff. The huff's also a radial algorithm. The other thing we have to think about is where we position the detector in the microscope. So as we get closer, and I show this with solid angle, we get more intensity at the center and less at the edges. It's a radial signal here. So as we get closer, we get more signal, but we get less signal at the edges. So really it becomes a balancing act to say, how do we do that? So we target 75 degrees because that's where we get a good mix between maximum intensity and useful dynamic range between the center and the edge of the detector. So that's where we aim for 75-degree solid angle. That position also allows us to get good 70-degree sample tilt. If we start to get closer than that, you start to worry about size of sample limitations. The other part to realize is that when we look at EBSD patterns, there's some baseline processing that's done to enable the band detection. So if we look at just what we call the as collected or live image, the EBSD pattern is typically a low contrast image, and it's the superposition of the diffraction signal on top of multiple different scattering signals as well. And so we see the intensity gradient from the center to the edge, and it's low contrast. So this is actually hard to find just the diffraction band positions. That's the huff space in that. And you can see there's a lot of noise, there's a lot of, we don't see the laser on the screen, but there's a lot of this waviness in there. So what we do is we use some background corrections to try to improve that contrast. And there's a number of different approaches we can use to do this. This just kind of shows an idea of the shape of this intensity in 3 dimensions. It's just a cool animation to show how steep that gradient is. And that's why the dynamic range of the camera is important, is we want to be able to get an image both from the center and from the edge to get as much band information as possible. So generally when we do this, we do what's called a static background processing, is we take a pattern, we take an area with multiple grains, we collect a signal where now that diffraction information is now averaged out. We just get the average intensity profile. We then subtract that and we get a corrected pattern. And really the trick with this is you want to make sure you get enough grains to average out the pattern to get a good background. But there's a number of other options that are available. Standard background subtraction has kind of been the historical norm. There's a background division. That works well when there's more intensity variations between phases. And then you can start to combine a number of these, as we can do both static and dynamic corrections with subtraction and division. So you can see there's a whole range of pattern quality that's available through the different backgrounds. And sometimes these are selected because at a small single crystal, it's hard to get a background, so you're forced to use dynamic. But there's a whole toolbox available in the software to pick the one that's going to optimize your pattern quality for your sample and application. And when we do this, we're able to add some normalization, contrast optimization routines that takes these here and sort of optimizes each one. So all of those now, we can automatically detect the bands with a huff transform and do the automated pattern indexing to really tackle all sorts of different materials. And then as we do this, we're extracting different metrics out of the pattern as we analyze them, in addition to just the orientation. We also extract what we call our IQ, or image quality. So if we look at these, not only can we index them, this is what the image quality map that comes out of each one of them is. So this is a sample that's a deformed tensile sample. It has a little bit of topography, but you can see the image quality value changes a little bit depending on which background's selected. So you have to use a little bit of care in interpreting these results based on how you're processing the pattern. And really the key takeaway is that we are doing image processing. Understanding what that image processing is can help interpret the final results that come out of the system. Now, the other thing that's important for cameras is realizing that the images can be noisy, and certainly as detector technology has improved, the noise levels have gone down, but understanding how the noise comes from the camera but also how that noise is influenced by indexing is important. And I talk in terms of noise because the signal level is generally constant when we compare some of these. So our signal to noise changes as well, but I talk a lot in just terms of noise. But high noise levels decrease indexing, or low signal to noise. And this is just an example from the camera as we turn up the gain on the camera, so we're amplifying the signal. When we amplify the signal, the noise, of course, goes up. We see that we go from a gain of 0 decibels up to 25. The noise goes from about 2 to about 10, and the patterns get worse. Well, this is an example that just kind of shows you how much noise can be tolerated. So in that pattern, that's a gain of 30 and a noise level of 15. You can see that's visually hard to see the bands, but we can actually index that with 99% success. The computer is very good at, machine vision type applications. That's what computers are really good at. So this quality of pattern, to your eye, you'd say that's bad. To the computer, that's actually good. And so we want to look to say, what can the computer tolerate, and also what looks good to the eye, because we want it to look good as well when we're doing things like phase ID and things. So there's a range we want to be able to operate the camera to facilitate that. But at some point, the indexing breaks down as the noise increases. So this is just a chart that shows noise on the horizontal axis and indexing success on the right. And you can see for materials, there's a point where it's working and then it starts to decrease. So the dual phase titanium one there is more difficult. It's a more complex structure. The bands are more complex, so it needs more detail to be able to resolve the orientation correctly. And there's also 2 phases, so it has to differentiate 2 phases at the same time. So that's more difficult. As it gets noisier, that starts to break down first. Something like a rolled aluminum is light. You don't get as much scattering signal, so it can't tolerate as much noise. A lower atomic number material, but not as deformed. So for us, understanding how much noise can different materials tolerate helps us design detectors that work on more materials and understand what speeds can we operate and still get the good results that we want. And it's important to realize that noise isn't the same thing as pattern quality. So this is just a little thing where the black line shows noise. The pattern quality is more dependent on band detection and strength of that band detection. So we're measuring a few different things and have to realize which one is which to best develop detector technology for EBSD. So when we talk about sensors then, we really want to look to say where are the noise sources that occur in the detectors. So the first one, what's called shot noise, and that's just basically a function of your signal level. And so generally this is fixed, and this is generally where EBSD operates. So the key thing for today's talk is in read noise. This is read noise based on the operation of the camera. This becomes more important as cameras become faster because we expose for shorter times. Our signal level drops, so read noise starts to be a more important component relative to the shot noise. And then there's the dark current noise, which is really a fundamental value from the detector itself. And that's lower than both generally from the way these are designed. But those are kind of your 3 primary noise sources. So traditionally, CCD sensors have had lower read noise values than CMOS sensors. And so it's only now that modern CMOS sensors have lower read noises and have become now a replacement for scientific instrumentation type CMOS cameras. CMOS cameras are an important technology because each pixel has its own dedicated electronics. CCD sensors, you shift things row by row into the readout circuitry. And so that acts as a sort of a bottleneck for acquisition speed. With CMOS sensors, now we can read out everything faster without a bottleneck. And so that allows us now, CMOS sensors can now be a faster acquisition sensor with lower noise than we had with CCD sensors. And then CCD sensors, we would do something called binning, where we would group pixels together to remove the number of reads we needed to get the image out of the sensor. CMOS sensors now can still be binned, but it's more to reduce the frame transfer bandwidth across from the camera to the computer rather than reading from the sensor itself. So we talk about binning. This is just a little example. We start with a certain array of pixels. We combine those pixels to create a smaller resolution image. Fewer pixels mean we have less data to transfer, and for CCDs in particular, you had to do this to get the frame rates. And this just kind of shows what we would get for CCD binning is that your camera would operate at one speed at one resolution, and you get faster images as you increase your binning for collection. So with CCDs, we kind of hit a plateau that we had to go to high binning values, in this case 12 by 12. So this was about 30 by 30 pixels, and we'd max out at about 1,500 points per second. And this technology, it's been out for probably 10 years or so, and the speeds have been available for 5-6 years of saying that's about the limit of what CCDs could operate. And so now with CMOS sensors, we've taken a leap up now to 3,000 frames per second or higher. And so that's where we've introduced what we've called our velocity camera. And so really the backbone of this camera is this high-speed, low-noise CMOS sensor that allows us to get greater than 3,000 index points per second while still hitting this 99% indexing success rate. That's sort of our target. We do this with a sensor that's 640 by 480 pixels, but we operate at 120 by 120 images, pixel resolution images, for that 3,000 points per second. And the reason that is one, it allows us to transfer via just Ethernet. Two, our Huff transform works well at that resolution. We go too high of pixels, it has more trouble finding the center of it finds things differently than at this sort of 100 by 100-ish resolution. So that's where we sort of targeted the operation. So I wanted to show some examples. This is our traditional benchmark sample. It's a nickel superalloy with, you can see in this orientation map here, so the colors show the orientations of each point. Within the different grains, there's some variation in color. So it's a deformed superalloy where we characterize the deformation and also the twin boundaries. You can see some of the twin boundaries in there. So it adds a benchmark of deformation, but also known misorientations. So we're able to say, is the system really working well for a variety of different characterizations? And if we go look at within one of these grains that's deformed, the color changes from one to the other. We can see the red distribution there, which is point-to-point misorientation. Our angular precision is actually quite low. We're generally, on our samples, we can get down to less than 1/10 of a degree change we can characterize. But that blue distribution, where we go from point to origin, shows that we're not just in a noise, we're actually characterizing the shape of that deformation across a grain through there. And we can do that just with our standard indexing. There's no special modes required to be able to characterize that sort of material. And one of the advantages, again, of using this CMOS is that because we're using this 120 pixel by 120 pixel image area, we're getting better orientation precision at these higher speeds. You can see the difference between a CCD sensor at high speeds and a CMOS. We have a lot more pixels. So because of that, we're finding the bands with more precision. That translates into getting this deformation characterization even at the high speeds. That wasn't as easy to get with CCD sensors. So taking that a little bit further, this is a deformed ferritic steel. So this is a BCC, body-centered cubic structure. The deformation is a little bit different, more deformation present. And again, we can get 99% success rates at 3,000 or above. And again, going through a line scan, this one I picked a grain that had 2 different bumps in it. And you can see our red line again is pretty well flat, but our blue shows the shape of how that grain has been bent through, in this case, a drawing process with no special modes required. So those are 2 different cubic structures. This is just an example now pushing the camera a little bit harder. This is an additively manufactured titanium 6-4 alloy where the collection is not 3,000, it's about 2,000. The success rate's a little bit less, 95%. That's just due to some points generally at grain boundaries, but we're differentiating 2 phases as well, a hexagonal phase and a body-centered cubic phase, so there's a little more calculations involved in that. So we still get high-speed characterization of multi-phase and non-cubic structures. And this just shows the phase map. So you can see the phase is actually identifying, these are small retained beta grains. So these additively manufactured materials, they're heated up to form one phase, and then as they cool, the remnants of the beta grain that was at high temperature shows up between these alpha laths. And so understanding the orientations and distributions of these beta grains is pretty important as you try to 3D print these alloys. As a fourth example, this is a dual phase steel with some sigma phase in there. So these we can index at about 2,500 points per second, around 99% success. This is for things like pipeline steel type applications. So multi-phase is still pretty high speed. This is looking at the austenite and ferritic phase distribution. So understanding how to thermally process this is important for optimizing corrosion resistance. This is just one, this goes back to one of the materials we had on that chart where on the noise chart, this is a rolled aluminum sheet we kind of use as a benchmark. So we're able to get 2,500 points per second at 96% indexing. And this is a 3D printed nickel superalloy. Again, a very complex microstructure. We actually looked at this on multiple different length scales with 99% success. So kind of can use it on a range of different materials. The other thing that it can be done is, of course, we can combine this with our EDS detectors. So our EDS detectors are also designed for high throughput, high efficiency collection. So this data can be collected simultaneously. So this just shows an example. This is again from a nickel superalloy, looking at some different, the blue precipitate there is a titanium-based carbide. The chromium are grain boundary precipitates in these grains. And so we've collected this at 3,000 points per second. We still get usable EDS data. So that's just an EDS map. But we can also use it for what we call chi-scan. Chi-scan is where we use chemistry to differentiate similar crystallographic phases. So in this case, there's a copper phase and there's an iron nickel phase. Both of them are face-centered cubic. What that means is that the diffraction bands for a given orientation are the same for the two phases. So it's very difficult for EBSD to differentiate those. The bands are in the same position. But chemistry, so this just kind of shows trying to differentiate it. So this is a phase map. You can see the phases are very noisy. It can't accurately differentiate those. But chemically, they're very different. So this is an EDS map here. So the copper is blue, the iron nickel is a greenish red mix in the middle. So because we can very easily distinguish these by chemistry, we can use this now to drive our crystallographic differentiation to get a phase map that looks like that. And in this application, it was important because the grain size between the edge and the center was very different. So we could correlate grain size to phase to spatial location. That's our new CMOS based velocity camera. And so the other thing I really like to emphasize with this is that the camera is coupled with the indexing technology. So we have what we call our triplet indexing and our confidence index values that not only do we index the pattern, we give some measure of reliability of that indexing. We call that our confidence index. So whenever I've talked about a 99% success rate, it's not only that we're indexing it with some degree of uniqueness and confidence to try to measure that. So we're coupling sort of proven technology with our EDS detectors as well as this new low noise, high sensitivity, high performance sensor for this velocity detector. The question in my mind then becomes, what do we use this speed for? When we talk about how speeds used to be, we used to collect 20,000 points overnight. And now we can collect it practically instantaneously. So the question says, well, what are we going to use this data for? What's the advantages to collecting a large number of data points versus small and that? And this is just an example I like to show for this. This is an aluminum film that has on average 2.5 micron grain size. And so taking different step sizes. So we have to determine how often do we want to sample. So on the left, we have a 25:1 ratio based on our grain size. So 100 nanometer steps, there should be 25 measurements on average along one axis and then along another. So we get a very pretty looking map there on the left. Then we go to a 10:1 ratio here, a 5:1, and then a 2.5:1. So obviously the maps start to look nicer just from increased pixel density. But if we look at it statistically in terms of texture, grain boundary structure, grain size, we're still pulling out a lot of the same data. It's really, if we're trying to measure deformation structure, then it becomes important trying to put that sampling grid along the deformation gradient to do that, but that's dependent on what spatial scale your gradients are. But I think it's an important question, and I don't know if there's a clear answer. Certainly we've seen, if you think about that chart I showed, speeds increasing per year, there's never been anyone who said, oh, we're fast enough. We don't ever worry about going, everyone likes to go faster. That's pretty clear. And well, I'll show some examples from in-situ type stuff where it's really important, but it's not always necessary. You can get the data you want very quickly. But it does, certainly there's talks in the symposiums where people thinking of sparse sampling and how to sample space. I think it's unclear yet how this fills into that role, but it's an active question of how do you sample structures efficiently versus oversampling. At some point you're saying, I'm just throwing power at it that maybe you don't need to as well. So I like to put as an example, this is a slice of an iron nickel meteorite. It's a famous meteorite. You can buy slices of it off the internet. But the important thing from my consideration is the spatial scale of the microstructure. So this is one that was collected, what we use, I call a combo scan. So we move the stage, collect an image, move the stage, collect an image, and then we montage it all together. So you can see this is on a centimeter scale type of a structure to look at this entire piece of meteorite. But if we look at it at higher and higher resolutions, you can see that within this, it's kind of a fractal problem. The closer you look in some parts, you start to see smaller and smaller structures. And there's actually, Joe Michael has actually done TKD on these to go down to nanometer scale fixtures. So it's really centimeter, nanometer scale microstructures. So with these kind of things, these fast acquisitions, you can start to think about saying, I can collect large areas with very fine resolution and have that all together. And so that's one area where it would make really sense to have the best of both of those together. The other place where speed's really useful is in 3D acquisition, where you're collecting a slice and then you're cutting something off and collecting another slice and then stacking that up together. As the cameras start to get faster and faster, EBSD becomes not the limiting factor. Of course, on the other side, on the microscope side, they start to make the cutting faster and faster. So, we're always trying to push to say, can we get these data volumes now faster than we could 5, 10, 15 years ago? So this is the same meteorite, and you can the numbers are a little bit scalier. This is a large scale 3D section, and it's running, it's just a second. So this is looking at the boundary from one of the large grains to some of that finer structure, just to show some 3D runs in it, between it. And you can see that shape of a shell through here. There's actually a phase boundary that goes through that. So that's what we see here. Instead of an orientation map, this is now a phase map, trying to look at the shape of this phase. I call it like a hole from a region where it cooled at a different rate than the larger parent grains. And so having a fast camera there is really pretty effective. And of course, everyone likes 3D maps spinning around. The other where it's useful, is important, is when we start to see dynamic changes in the microstructure. So this is a 2D example of just in-situ recrystallization in a material. So the faster we can do each time slice, either the larger the area or the shorter time we can actually take a slice to watch, in this case, recrystallization. And this is the same material that was then stopped midway doing a 3D reconstruction, just to look to say, what are my recrystallization nuclei in 3D versus the deformed microstructure. So I tongue-in-cheek called that 3.5D analysis, but it's just another way of trying to say, how can I characterize more of a microstructure where having, the danger, of course, in zooming in on a small area is, are you getting a representative sample of the real thing? So if I'm able to look at larger volumes, I can compare to see, are all these recrystallization nuclei behaving the same way? Does that tell me something of interest? And the other one would be, of course, a deformation experiment. So this is just kind of showing along a stress strain curve, different places of collecting data, and then collecting an orientation map at different levels of deformation. If we're able to do this faster, we're able to avoid drift issues. The speed can really help with dynamic type measurements. So that's our velocity camera and what I'd call our traditional hardware design. So with this, again, remember we have a number of different components. We have a phosphor screen that converts the electrons to light. It's important for us as we develop technology to realize that phosphor efficiency is energy dependent. And then the light travels through the glass, travels through a vacuum seal, travels through a lens. There's losses involved along each step of that. And then these sensors, there's been improvements in sensitivity and noise, but there are losses. There's only a certain amount of efficiency that's built into the sensor. So that leads us to looking away from light detection to direct electron detection. And this is, of course, a technology that's been used quite extensively now in transmission electron microscopy, saying, can we translate that same technology for SEM-based EBSD detection? And so the idea is we remove some inefficiencies from the process, we get rid of distortions from the optics, we get rid of blurring from the phosphor screen, we get higher efficiency collection, and no read noise. We get better results at low beam dose applications. So we're exploring this technology for EBSD and wanted to talk a little bit about it. So this is just a high quality direct electron detector pattern from silicon. So you see it's a nice, very pretty pattern. And if we look along some of these bands, so some of those bands you see how there's stacks of lines, those are higher order diffraction lines. So if we look at the detail in those bands, we see compared to CCD based imaging, the detail and contrast in those lines is significantly higher than with traditional detection methods. So for us, that was encouraging to say this could bring some new opportunity. This is just putting the DED pattern next to a CCD-based pattern. So there's a lot more detail, there's less blurring, better image quality measurements that says the DED has significant application possibility for things like high angular resolution EBSD and for phase identification. This just kind of shows the operation, different conditions. So this is sort of traditional 20 kV standard EBSD operating conditions where we're getting 8 times more signal with improved sharpness, especially along the whole array of the detector. We don't have to worry about lens performance radially as much. We get sharper images. And as we drop the voltage, this goes down to 10 kV. Again, we're getting more signal, better quality at lower voltage as well. The phosphor energy dependence, it's more significant at lower voltages. And this kind of shows the same thing away from silicon. This is at nickel, 20 kV. 20 kV at faster speeds. This is 100 fast is relative. This is 100 frames per second to start. And this is dropping to 10 kV. And this is actually going down to 5 kV. And that's where we're technology looking to say, can we go 5 kV or better? But you see we end up with 22 times more signal at lower voltages. So it starts to say, is low voltage EBSD something of potential interest for spatial resolution? So, and then in addition to just single pattern collection, we also can start to think about doing orientation mapping. This is on a perovskite photovoltaic film where there's beam sensitive samples, so that can't handle typical beam currents used for traditional sensors, but you can run at lower beam doses and still get diffraction pattern and not basically melt your crystal. The other application that has a lot of promise with this new type of detectors is the HR EBSD. This is what's called the Wilkinson method. Angus was just walking around a minute ago. I told him he wouldn't be interested in this and then realized that he might have heard his name. But this is where we compare one pattern to the next, looking for very small sub-pixel changes in the positions of the diffraction information. So what's done is within each pattern, there's a number of different regions of interest that are displayed. Each region of interest is compared to another via a fast Fourier transform cross correlation. Again, looking for sub-pixel shifts in intensity. And we do that for all those ROIs to calculate what's called a displacement tensor. So we're able to figure out both the elastic displacement and the shifts in rotations in the patterns. So this just shows for the direct electron detector, we can place a bunch of ROIs in different areas there to compare differences. We move the beam along there, so this should give us systematic shifts in the pattern. We can measure those shifts, we can do fitting to those shifts, and for us, the result basically comes back to the worst case is 1/40th of a pixel. The best is better than 1/80th. With phosphor-based technology, we're typically at about 1/10 of a pixel. So we've said we're probably at least 5 times better performance in terms of measuring these displacements than phosphors. And again, this is because of fundamental blurring of the phosphor, sharpness of the lens, everything. The DED gets rid of those fundamental limitations and allows for more precise measurements of these shifts. There's also, taking this a little bit further, and a couple of different ideas is, rather than comparing one pattern to the next, can you compare one pattern to a simulated pattern and then iterate to find the best fit? So this idea of comparing a pattern to a simulated pattern, when we simulate the pattern, to get the best fit with an optics-based system, you really should be simulating the lens, simulating the phosphor. All that turns out to be pretty difficult to simulate well enough for this to always work. So by being able to get rid of that, we can start fitting simulations quite better. So this just shows an example of an experimental pattern, a kinematic diffraction simulation, and then the dynamic simulations that are becoming more and more available and faster and more usable. Another application is the dictionary indexing, where for a given sample, we create what we call a mastered pattern of all orientations. We throw that into a library. We then take a pattern, compare it to all the patterns in that library, and find the best match. This just kind of shows some of the indexing. So as your patterns get worse, your dictionary indexing, your pattern matching actually works pretty well. And there's a number of new applications in terms of pseudosymmetry resolution, accuracy, being able to determine reflectors, where this ability to match to a pattern has some unique applications. And so as our detectors become better, our matching becomes better, so these applications become more and more applicable. So as just a summary for direct electron detection, again, we almost like to call it zero noise, but that's a little misleading because they're still shot noise effects. But low noise, distortion-free patterns. We don't need to worry about the lens distortion, phosphor specs, and so for strain, absolute strain, dictionary indexing, expect a step in performance that's going to be available through direct electron detection. As a summary, the CMOS sensors enable high-speed, low-noise detection. We have a velocity camera that provides greater than 3,000 points per second with high reliability in the data. There are demonstrations available if you're interested. And then the direct electron detection will be able to provide higher quality, lower noise, distortion-free imaging that we think there's going to be applications with pattern correlation as well as other applications.